Hello everyone and welcome to another math video. This time we are going to cover a topic in calculus. That topic is differentials. And what we do here is we use differentials to help with tangent line approximations, as well as we will compare what dy and delta y mean, aka we will look at error propagation. And of course, I have to, at the very beginning, go over what is a differential. So let's get into that. What do these symbols mean? Well, here we have delta x and delta y. And those are very much the same symbols you remember from maybe a college algebra, algebra 2, pre-calculus. It's just some change in x and some change in y. And these represent the actual change of x and y on the function f of x. Now dy and dx are what we have been talking about in calculus in terms of derivatives. What dy and dx represent are a change on a tangent line of f of x. So to bring more light to that, here is how we can look at a particular function and sort of define better what dy and dx are. So here I have a function, this black curve function here. I'm going to call this f of x. And if I just take any random point along this function, say this point right here, at the x value c, I can find the y value that is paired up with it in its ordered pair by simply substituting c into the function and getting f of c. So this ordered pair here is f of c. Alright, so delta x, as you can see down here, delta x is some change in x. It also consequently is equal to dx, and I'll get into that a little later. But for now, on this function, if I move over to the right some specified amount of x, some change of x, the x-coordinate now becomes c plus delta x. And if I follow it up to the function, the point is right here. The y-coordinate that is associated with this x-coordinate I can find just by substituting this into the function. So I can substitute c plus delta x here, it would be f of c plus delta x. So you can see now the vertical change between f of c and f of c plus delta x, I'm going to call delta y. And I'm going to put that way down here at the bottom. Delta y, this is the actual change, the actual vertical change. Delta y will equal f of c plus delta x minus f of c. And this starts to look like how you find the slope of a tangent line using the limit definition. Remember doing that? All right. So again, this just represents vertical distance. All right. So now with the tangent line, let's go back to our point c f of c. There we go. We can find the equation of the tangent line here. We can draw in the tangent line and it would look something like this. And if I go over that same distance, you'll notice that we end up at the same x-coordinate. So for right now, I'm going to follow this up to the tangent line, and I'm just going to call this point x comma y for now. I'll get into it in a little bit. So here, this distance between the original point of tangency on the function and this new point that is to the right, delta x, is y, the y coordinate for this point, and we don't know what the y coordinate for that point is, we don't have enough information, and we would take away the original y value here. And that's what we would call the differential of y, or dy. This is the change, the vertical change from this point to this point on the tangent line. And you can see it's not the same as delta y. But what we will end up doing is we will use dy to approximate delta y. And the reason we do that is because while this point might be easy to figure out for a given function, finding the y coordinate for this point could be pretty difficult. But in a lot of those cases where finding the y coordinate here could be pretty difficult, we can easily approximate it using a derivative. Let's see how that works. So I'm going to start with the point slope form of an equation. And I'm starting with the point slope form because we will be using the tangent line to approximate a delta y value. So from here, I'm going to use the point of tangency as my x sub 1, y sub 1. So the new function will look something like this. Substitute c in for x1, substitute f of c in for y1, and we get y minus f of c equals m times x minus c. From there, we can also substitute the value of the slope in this equation, because the slope of the tangent line is what we would get if we find the derivative of f and substitute c. So the slope of the tangent line here would be f prime of c. Now to make the point that dx and delta x are the same distance, if we go over delta x, and that will get us to the point on the curve, but we want to have a point that is directly above, or it could be below depending upon how the tangent line sits. We want to have a point directly above or below it, and since we're talking about the tangent line, it would be dx, then dx and delta x have to be the same. So we will not be using delta x in our calculations though, dx in our calculations though. We will be sticking with delta x. So this x coordinate up here in the purple point could have been written as c plus delta x. But the y coordinate here is still just y. We have no idea what that particular y value is at all. So since the x coordinate is c plus delta x, that allows us to replace this x with c plus delta x. And then we will have minus c, and the rest of the equation is unchanged. So now we have something that is very, very awesome. We have these c's will reduce away, leaving us with the equation y minus f of c equals f prime of c times delta x. And if you come back over here to the graph, you can see that we already defined dy as y minus f of c, which is exactly what we have here. So y minus f of c, we now just proved, is equal to f prime of c times delta x. f prime of c times delta x is how we will approximate our dy, which again is an approximate change in y. And we are going to use this approximate change in y to pretty accurately estimate the actual change in y. So what is the definition of a differential? Well, here we have exactly what it is. Let y equal f of x be a function that is differentiable on an open interval containing x. So the definitions are, we have a differential of x dx is any non-zero real number. And we have the differential of y dy is equal to this equation here. Dy is equal to f prime of x dx. Now, in order to have a slightly better understanding as to what's going on, I want to look at this equation that we started with way up here. Y equals f of x. So, if we take the derivative of both sides, we would get dy over dx equals f prime of x. Now f prime of x, this derivative just tells us slopes of tangent lines. So on the left side, this dy dx tells us how much the vertical distance of the tangent line changed compared to how much the horizontal distance of the tangent line changed. More or less, the change in y over the change in x, but in terms of a tangent line, like derivatives tell us. So if we wanted to find just the change of vertical distance, we could think of it like this. This isn't mathematically rigorous or anything like that, but you can think of this as multiplying by delta x, and now you have dy equals f prime of x dx, which is exactly the definition of the differential of y. Furthermore, if you're trying to find the change in vertical distance at a specific x value, call it c, then we can substitute c in for x, and knowing that dx is going to be the same distance as delta x, we can replace dx with delta x, thereby getting to the result we got on the previous slide. And one last thing here. We said the differential of x dx, or delta x, is any non-zero real number. Why is this part of our definition for dx? Well, it's because we cannot divide by 0. So dx has to be some actual change in horizontal distance between 2 points. Otherwise, if there's no horizontal distance change at all, then why do we need the tangent line to even approximate what the function value was? One last thing is that when we are approximating values using a tangent line, we want the point of the tangent line, the point of tangency, to be very close to the area or the y value we are trying to approximate. We don't want this dx or this delta x to be very big at all. We want them to be within maybe 1/10 or 1/100th of a unit to the value we are trying to approximate. For our first example to see how this works, we will find the tangent line approximation to the graph of f at the given point, and compute the table. So the table I'll get up here in a minute. The function I want to get up here first. We will have f of x equals x squared at the point 2, 4. So all we have to do here is first find the tangent line for this function at this point. So all we have to do then is find the derivative, substitute 2 in for the derivative. 2 times 2 is 4. And this is the slope of the tangent line at x equals 2. So the equation of the tangent line is y minus 4 equals 2 times x minus 2. Apologies, this is 4 times x minus 2. There we go. The slope is 4. I just found that out. So if we want to make this easy, we want to solve for y. So that'll include distributing this and getting 4x minus 8. And then adding 4 to both sides. 4x minus 4. So here is the tangent line with which we will use to approximate our values. Now let me get the table up here. So here we go. We are going to first run all of these values for x through the tangent line function and figure out what we get here. So when you take all of these x values and you substitute them into the tangent line function, you'll get all of these y values back. Now, to see how close we get, or how close this approximates the actual function, so I'm going to circle this one in blue, or box this one in blue, and say f of x equals. So when you substitute 1.9 into this function here, you end up with 3.61. And when you substitute 1.99 into the original function, you'll get 3.9601. Guess what? When you substitute 2 into the original function, you get 4. Right? I said that if you don't move to the left or to the right any amount, then there's no reason to use the tangent line to approximate the function. These values here are pretty close to these values here. So we can, in a small neighborhood around 2, like 1/10 away or 1/100th away, we can use tangent line approximations to pretty accurately represent the real function values. These other two values over here are 4.0401 at the x value 2.01, and you can see how close they are, and 4.41 for the x value 2.1. And again, that's still a pretty good approximation. So for the second example here, we are going to find the tangent line approximation to the graph of f, this time being, everybody's favorite trig function, at the given point, and complete the table. So again, the first thing we want to do is find the derivative. So f prime of x is negative cosecant x cotangent x. Then what we can do is we can find the slope of the tangent line here, f prime of 3, is negative cosecant 3 cotangent 3. And to keep the values exact, we will be using this as the slope. And I do apologize if you can hear a snoring dog in the background. The next thing that we want to do is set up our tangent line, right? It's going to be y minus the y value of our ordered pair, cosecant 3, equals the slope, negative cosecant 3 cotangent 3 times x minus 3. Lastly, if we can solve this for y, we will get y equals negative cosecant 3 cotangent 3 times x minus 3 plus cosecant 3. And if you wanted to be really fancy about it, you could factor out a negative cosecant 3, leaving you with a cotangent 3 times x minus 3 plus 1. So this is our y. And what we will do then is we will be sure to put a table over here and get to approximating. So here we have our x values that go a little bit to the left and a little bit to the right of 3. And just like in the last example, I'm going to substitute each of these x values in for x here, y being the tangent function, and I will calculate a decimal approximation as to what the y coordinate would be near 3 for cosecant of x. So before I go too much further, I realize I made a sign error here. If you common factor a negative cosecant 3 here, this will be a negative 1. I caught that error before I made my calculations. So if you go through and substitute these x values into the tangent line function, the y equals, you will get these corresponding y values. Now I'm going to take all of these x values here and substitute them into the original function to see how well this tangent line approximates the actual function values. All right, here are the real values. And you can see that, of course, as expected, if you substitute 3 into our approximated function and you substitute 3 into the original function, you will get the same value. There is no difference in x, so there shouldn't be any difference between our calculated value from the point of tangency on the tangent line and our calculated value from the point of tangency on the original function. However, when we start moving away from 3, you can see that there are some differences here. You can see that there are some differences here. But these are still pretty close to each other, no problem. But when even we get just 1/10 away from 3 going to the right, there's a huge error here. The function value is almost twice as big as the tangent line approximation. And the same thing over here at 2.9, 1/10 of the way, 1/10 in the other direction. The function value is about twice as big as the tangent line approximation. And another thing I want to state is that we can't go past 3.142 here, because the original function, if we took a look at the graph of this cosecant, it would look something like this. At 1 and pi over 2, we would have a point there, pi over 2 comma 1. At 0 and pi, there are vertical asymptotes, and the cosecant function looks something like this. So if we had gone past 3.1415 if we had gone past pi, we would have gotten negative numbers over here, and that would not have been good. So we have to make sure that we are being cognizant of these values for x. And these values will be given to you. But because as we go from 3 to 3.1, the graph is approaching a vertical asymptote, so that means these values are going to grow very quickly. Whereas the tangent line approximation, they just grow linearly. And the tangent line approximations don't care about vertical asymptotes. They will just keep going. The same thing going to the left. It's way off because the graph is not decreasing to the left as quickly as the tangent line function is. Let's take a look at one more example. This will be the last example before we get to error propagation. So we will use the information to find and compare dy and delta y. So what you will be given is a function, an x value, and the delta x slash dx. So what you want to remember here is that dy is equal to f prime of x dx. And for a specific x value, which we can call c, in this case 2, we can find dy by multiplying f prime of c times dx, or as I defined it earlier, f prime of c delta x. So that being said, all we have to do is find the derivative at c equal 2. So f prime of 2 is negative 4 to the third power, but we'd have to have 2 in this set of parentheses, which would be negative 32. So this is f prime of c. We also know that dx is 0.001, which would lead to a very easy multiplication here. Negative 32 times 0.01 is negative 0.32. So here we have found the change in y along the tangent line between 2 and 2.01. That change in y is negative 0.32. To find delta y, which I'll do in blue down here, all we have to do is subtract f of c plus delta x minus f of c. And so from this particular equation here, all we have to do is find f of c. In this case, substitute 2 into our function. So 2 to the 4th power is 16. 2 minus 16 is negative 14. And we can substitute c plus delta x. 2 plus 0.01 is 2.01. And we have to substitute 2.01 into our function here. So once you substitute 2.01 in for x, you'll get negative, and raise it to the fourth power and take it away from 2. You get negative 14.3224. Then the negative 14 here becomes positive, and when you combine these two, you get negative 0.3224. So you can see how close these are to one another, and how relatively accurate you can approximate the actual change in y using the slope, using the tangent line. And that's because we are picking values that are very, very, very close to x. Let's take a look at error propagation. Error propagation. For error propagation, we are basically going to be finding delta y. Delta y is what we will call the propagated error. In order to find delta y, we go back to our original definition for delta y described a few slides ago. For whatever x value we pick, call it c, we can see that how very quickly this equation would become delta y equals f of c plus delta x minus f of c. So with this, we have f of x plus delta x minus f of x, where x we would say is the measured value. And because when we humans measure things, we by definition get it wrong. There is some assumption of error when we measure things. So what we do then is we add to that some small value of error in measurement. And if you add the measured value plus the error in measurement, you would get the exact measurement. So when we look at f of x plus delta x, this is what it's supposed to be. And this is what we measured it to be. So when we find these values here and here and substitute them into the actual function, we can find out what the propagated error is. Now, in order for us to estimate the propagated error, the delta y, we can use the derivative as we have done in the past. So delta y can be approximated by dy. And you've seen if we can make the error small enough, if we can make this delta x small enough, then the approximations from the tangent line end up being very, very accurate. So when we start looking at all of this delta y is being approximated by dy, that means we have to take the derivative to approximate the actual change in y. So we will be using dy equal to the derivative times dx, which in this case we will know what the dx is. It is equal to the delta x that we will be able to pick out in the actual example. All right, so let's take a look at how we can do this. For our final example here, we will have an example of propagated error, and we're given the radius of a spherical balloon is measured as 8 inches with a possible error of 0.02 inches. use differentials to approximate the error in computing the volume. So once we can remember that the volume is 4/3 pi r cubed, we can find the error dV, which we will need to approximate the actual delta V, by taking the derivative of the right side of the equation, 4/3 pi times 3r squared. And normally we would have a dr over here underneath, but it's going to be over here on the right hand side, because in order to approximate the actual error delta V, we will need dV, which will be the derivative of the volume function, with 8 substituted in for r, and the possible error substituted in for dr, which again is also equal to delta r. There we go. So what we can do then is what I just said. We can substitute, actually I think we can do this first. Let's reduce these 3's with one another, and then get a right hand side of this equation to be 4 pi r squared dr. So substituting values in is pretty simple here. We have 4 pi times 8 squared. But when we substitute the value 0.02 in for dr, we don't know if that error is an error that was bigger than 8 inches or less than 8 inches. So we have to represent the fact that we don't know with a plus or minus 0.02. Now the last thing that we need to do is just multiply all of this stuff together to get 5.12 pi with a plus or minus in front. Again, we were not given whether our estimation was high or low, higher than 8 inches or less than 8 inches. So we have to go both ways. The balloon could be 5.12 times pi inches cubed bigger than what it should be, or less than what it should be, or anywhere in between there. So now we can do the same thing, but let's talk about surface area. So the surface area of a sphere is 4 pi r squared. And again, if we were going to find the error of the surface area, we would have to find the derivative of this function, which would be 8 pi r times the error that we think is there, 0.02. So again, we can just go through and do this calculation. So the approximation for the error here, dSA, the differential for the surface area, would be 8 pi times 8 times 0.02, which is 64 pi times 0.02, which is 1.28 pi inches squared this time. And in fact, we would have to have a plus or minus in front of this 0.02 and this 1.28 pi inches cubed, because we don't know if that error is bigger than or smaller than the 8 inches. The last thing we can do is approximate percent of error. So what we can do to figure that out is take dV, so we'll focus on the volume first. So let's see, percent error, you take dV and divide it by V. So what that would look like before anything is done. You just want to go back to the actual equation. So dv is equal to 4 pi r squared dr. And v is 4/3 pi r cubed. So you want to go back to the actual equations before any numbers are substituted in, because it'll be easier to see how things reduce. So I can reduce the pi's. I can reduce an r squared here with 2 r's down here, leaving me with r to the first. Heck, I can even reduce these 4's. And when I simplify all of this, I will end up with this 3 in the numerator. We will end up with this simple expression. So the last thing that we need to do here is substitute our values in. 3 times all over 8. Again, this is a plus or minus 0.02. And what we can do from here is calculate what this would be, or approximate what this would be. So this would be 0.06 with a plus or minus all over 8, which is 0.0075. And if you want a percent, you move the decimal point 2 to the right, and that is 0.75%. So we're doing pretty good on our approximations. If you wanted to do the same thing for the surface area, you could. Again, you would always put the differential of the surface area over the actual surface area equation. So the differential here would be 8 pi r dr over 4 pi r squared. And you could see still that there would be a lot of canceling here. This 8 would divide in, the 8 and the 4 would reduce to a 2. We can take an r from there. The pi's are canceled. So here you are left with 2 dr over r. And again, you can substitute the values in and get, let's see, it would be plus or minus 0.04 over 8, which in fact, when you divide this out, would become 0.005, or as a percent, 0.5%. I hope this helps with your understanding of differentials and propagated error. Good luck.